Hello students, welcome back to another lecture on classical mechanics, especially the lecture number 19. In the previous two lectures, we have seen the Hamiltonian calculation and the evaluation of the Hessian matrix, which happens to be the demanding requirement for the successful calculation of Hamiltonian. So the point to be noted in the calculation of the Hessian matrix is that only for the simple systems, or at least where the constraints are limited to a minimum, it is possible to easily evaluate the Hamiltonian using the Legendre transformation. Okay, this is an important point because we have taken an example which is fairly simple, and then we have demonstrated the methodology of calculation. So the purpose of the previous lecture was to only see how to apply the Hessian matrix and then determine the possibility of successful transformation. So that was the main thing. In practice, what happens is calculation of the Hamiltonian is not that simple. Okay, so the important point to be noted is that the more the number of constraints a particular dynamical system will have, then you will be having more coupling will be there between the velocities. Okay, and therefore what happens is that the calculation of the Hamiltonian becomes complicated even if the Hessian matrix is non-singular. So if the Hessian matrix is singular, then straight away you can't calculate. So that is the situation. But even otherwise, the more the number of constraints on a particular system, then you will be having more difficulty in evaluating the Hamiltonian. So these are the downsides of the Hamiltonian method. But however, what is the strong side of the Hamiltonian mechanics is that it offers a possibility to understand the physical system in terms of the geometric properties of the phase space. So that is where the strength lies actually. Okay, so mathematicians are more interested because it provides an opportunity to learn the properties of mathematical space called the phase space. So phase space is a mathematical space. So studying the mathematical properties of such a geometric phase is of interest to mathematicians. And therefore this particular subject, namely the Hamiltonian mechanics, provides a very good platform to explore the properties of higher dimensional mathematical space. So that is one of the primary reasons for the development of the subject. And in fact, even today, there are many people who work towards a doctorate degree in Hamiltonian mechanics. So therefore, the topic is in fact quite active. But the point to be noted is that such kind of practical works will deviate from simple paper and pencil calculation. Most of the time, inverting procedure requires much of the computational effort in terms of matrix inversion. So ultimately what happens is Hamiltonian will become a matrix. Okay, it can't write down as a simple expression. So these are the practical difficulties. But ultimately the point to be noted is that in any case the Legendre transformation requires the procedure for the inverse function, and therefore it is always a good practice to learn how to write down the Hessian matrix for a given problem and then identify, because at least for the purpose of the gate examination and for the net examination, CSIR NET examination, the procedure for the evaluation of the Hessian matrix is quite important, and therefore you will have to practice one or two problems for this. So now in continuation with whatever we have done in the last class, now we are ready to make a Legendre. So that's what I have written here. You can see we are planning to take the Legendre transformation for a possible simple case and then take the Lagrangian to be t minus v. So what is the purpose is that after finishing the calculation, we will be able to realize that the ultimate final expression that we are going to get will be the total energy of the system. So the point to be noted here in the today's work is that it is not a hardcore proof or what you call the solid proof saying that the Legendre transformation of the Lagrangian is the total energy. So that's not the proof. Okay, so such a proof is not there. The point is that Lagrangian itself, here you'll have to follow the white cursor which I am showing on the screen. If you remember our previous lectures, we have explained that a possible expression for the Lagrangian is T minus V, where T is kinetic energy, V is potential energy. So it's only a possible expression for the Lagrangian. And what are we are going to do is we are going to take the Legendre transformation of that, which means that, so the point to be noted is that you can't say that Legendre transformation of the Lagrangian is the total energy. Such a statement is not valid. Okay, because Lagrangian itself is not unique. You can choose any other function instead of t minus v. So this is one important point. So what happens therefore is most of the situation, that's why this particular word you'll have to see. So most of the situations the Hamiltonian will represent the total energy, but it is not a necessity. So in all the 100% of the situation, you should not think that this will be true. Okay, so Hamiltonian could represent total energy in many of the systems, but remember Hamiltonian may not represent total energy in some of the system. So both chances are there, and therefore we will now at least say that in as much as we are going to discuss the simple situations, and in cases where we are going to consider t minus v as the Lagrangian, in such a simple situations, at least we can realize, or at least we can feel that the Hamiltonian is representing the total energy. So that's the point to be noted. It is not that ultimately we are making a conclusion that Hamiltonian means total energy. That is not the conclusion. Hamiltonian can be total energy is okay. Hamiltonian is not always total energy. So that is the that point or the distinction should be clear to you. And with this idea, let us therefore consider a simple situation. So I'll write down A here. We are going to consider some Lagrangian for a most simple case, so that the purpose is that we are not interested to do complicated calculations, but rather we would like to see the total energy, how it is emerging. So the simplest situation that you can consider is a particle that is freely falling. Okay, when a particle is freely falling, you can write down the kinetic energy as half mv square, which you can write it down as half mx dot square. So that will be the kinetic energy. Then minus the potential energy. You will have to for potential energy, well, you need some reference line. So let me therefore draw here. So if this is the ground that you are going to have, in this particular case we will say that the potential energy U, so U will be equal to 0, and we are now considering a particular mass m, which is falling freely down towards the ground. So the speed of this particular thing will be changing, but whatever be the case, at any instantaneous time, the kinetic energy would be given by half mx dot square. So it is a free fall. It's a very simple free fall vertically down, and therefore the potential energy at any given instant of time will be equal to mg into h, where h is the height. And if you are going to consider x is the variable, so rather than saying h here, we can say x. And so this is how you can write down for the simplest situation. And in a typical classical mechanics notation, which means that in terms of q dot, if you want to write down, we can now write down like this, half into mq dot square. Then you have minus mg into q. So q would be the one-dimensional, a single variable, because there is only 1 degrees of freedom. So this is the simplest possible Lagrangian that you can think about, and therefore you have a t minus v is specifically or clearly visible here. So therefore let us now quickly calculate the Legendre transformation of that, and for that you will have to define the generalized momentum, which is given by dou L divided by dou q dot, and this must represent the momentum for the particle, and let us calculate this. So this will give you m into q dot. So m into q dot will be the expression that must be equal to p, and this means the inversion step is quite simple, which means that the q dot is equal to p divided by m. So here this is the place where you are going to pay the attention that q dot is equal to p divided by m happens to be so simple equation. You can see that the expression is so simple in the sense what do you mean by simple expression is you are able to separate q dot on one side and p on the other side, which means that q dots can be expressed in terms of p. Okay, such a situation is not always possible, especially when trigonometric expressions and logarithmic expressions, certain things will come into picture. Okay, in such a situation you may not be able to express all the time. For example, if you are going to have say if I am going to get the logarithm of p plus, let us say, q dot, okay, will be equal to, if I get sine of q dot, for example, Okay, if you are going to get a complicated expression where q dots are present on both the sides, okay, such kind of transcendental equation typically, okay, you can write any transcendental equation, which means you have a combination of algebraic expression, trigonometric expression, logarithmic expression, and e to the power expression. If a mixture of them is there in a single expression, separating the q dot on one side and writing the p on the other side is not that simple. That is what I mean to say. Solving a transcendental equation is not simple, which means that you'll have to go for a numerical solution. So this is the place, this step where I put a box here. No, this is the place where the inversion has been taken place successfully, and you are able to write down q dot on one side and p will be on the other side. Okay, suppose if you are going to say a very simple expression like sine of q dot is equal to p, if this is the equation, then you can write down at least q dot equal to sine inverse of p. So this is we say that this is also successful. But when situations are like this are coming, or if you are going to multiply with this expression with p, for example, if any kind of combination more complicated than this is going to appear, then you will realize that writing an expression like q dot on one side, p on the other side is not possible. So typically this kind of difficulty is what is expressed in terms of the Hessian matrix, where it goes to the the singular value of the Hessian matrix, I mean the determinant. So this is one thing. Second thing is that in many situations for textbook problem, I mean to say that within the limits of your classical mechanics course, there is one interesting thing that has to be noted down, so that you'll be at least feel happy that the calculation is reasonably good. So what is interesting in most of the problems that we are going to get within this classical mechanics paper or class is that the kinetic energy term is most of the time it is going to be half mx dot square. Most of the time you will be having an expression like this for kinetic energy. So this is always quadratic in nature. Quadratic, right? It's power 2. X square is there, right? That is a quadratic expression. Okay. So there is interesting point about this quadratic expression is not only quadratic expression, this is always greater than 0, interestingly. Okay, this is not true mathematically, but in physical situation this is true. So why it is always greater than 0? You know that 1 by 2 is a positive number. Mass of a particle is always positive. You don't have negative mass, right? And then when you are squaring this, velocity can be negative, but the square you are taking, right, and therefore that must be a positive number. So what happens is that this, because of the quadratic nature of the kinetic energy term, the interesting feature that is going on in the physical system is that this particular term is always greater than 0, and mathematicians use the word positive definite. So there are certain theorems and the corollaries which is going on in the theory of convex functions. In the convex functions are used to construct the Hessian matrix and find inflection points and so on. So in that theory, if you read carefully, mathematicians use the word positive definite. What do you mean by positive definite? It is definitely positive. That's all about it. So definitely positive number means what? Greater than 0. That's what I'm trying to say. So positive number means it's greater than 0, at least not 0. If it is 0, you can't say it's positive or not, isn't it? So at least you can say that it will be greater than 0, because when you are talking about the dynamics, something is moving, right? If nothing is moving, then velocity is 0. So since it is a dynamics, it is moving. When it is moving, velocity is greater than 0. In all situations, you will be having half mx dot square would be greater than 0. So therefore, positive definite means it is definitely a positive number. So whenever the term or term means the Lagrangian contains the kinetic energy term which is positive definite, then in most of the situations what happens is the conversion from the Lagrangian to the Hamiltonian is going to be successful in most of the situation. So the complication mainly arises because of the constraints. That's why I used to say when too many number of constraints are there, for example, double pendulum is there, you have at least many constraints are there. The second pendulum cannot oscillate so freely. Okay, it has to depend on the first pendulum's angle and so on. Similarly, if you are going to connect more number of pulleys, we have done a pulley problem. If you are going to connect more number of pulleys and then the arrangement becomes more number of constraints are there. So the more the number of constraints that are there in a dynamical system, then Hessian matrix will not go to 0. Okay, even otherwise, that is the difficulty which I am telling, that even when the Hessian matrix is not going to 0, the calculation of the Hamiltonian becomes a little complicated. That's what happens. But otherwise, what is interesting is within the physics, what happens is that because of the quadratic nature of the kinetic energy, this term is positive definite, and therefore it is definitely positive number, which gives you a great confidence that Hessian matrix going to 0 is not easily going to happen. Okay. So it will happen, of course, in a non-physical situation, such as, for example, population dynamics or financial dynamics, something like that, where we don't have a kinetic energy term like half mv square. In such a situations, you don't know what kind of expression is going to come, and therefore there is a possibility for the Hessian matrix determinant going to 0. So the point to be noted here is that within the structure of the physics or physical systems, it is most probable that you don't have a straightforward situation where the Hessian matrix will go to 0. That will pose the problem. Okay, but however, difficulties are there in evaluating the Hamiltonian itself, as I explained. So that is a point to be noted. So the inversion step is the one which I would like to express here. So because of the simple equation in our case, this is the inversion step. Okay, that happened to be so simple that you don't even realize that we are inverting it. Okay, that is what I am trying to say. The equation is so simple, and you are rearranging and writing, you don't even feel that we are performing the inversion operation. Okay, that is why I am trying to express by putting a box here and saying that this is the step for inversion or finding the inverse function. Okay, so once this particular intricate topic is clear, then the rest of the thing is to write down the Hamiltonian definition, namely that we will have to write down P into Q dot minus the Lagrangian, where since we have only 1 degrees of freedom, there is only one P and only one Q, and therefore the situation should be simple. So now what we'll have to do is that we'll have to substitute. So P into Q dot minus the original Lagrangian happens to be half into m into Q dot square minus mg into Q. So now what we'll have to do is you'll have to replace all the Q dots by P. So now only we'll have to use this expression, the inversion expression, remove all Q dots and then bring somehow an expression containing P. So in our case, the expression containing P is P by M. So let us do that. So that will be equal to, so this is P into Q dot is actually P by M. Then you have minus open bracket half M P by M square minus, in the potential energy term, generally there is no involvement of the the velocity, namely the dots. So this is another place where troubles can come. You already know that whenever the potential energy contains the velocity, if the potential energy is containing velocity, such potentials are known as velocity dependent potentials, and they are going to give a lot of problems in the solution, and sometimes it will be too complicated that the system itself will go to non-holonomic. So those situations are there, but even if it is not going to non-holonomic, it will pose considerable amount of mathematical difficulty, because in the potential energy term also you will be having the Q dot means that also you'll have to replace when you are performing this Hamiltonian transformation. So these are the places where difficulties can arise. Okay, so if you are going to simplify this expression right now, we'll be having P square by M minus, this is actually P square by, so this gives you 2M, then minus of minus is plus, then we get mg into Q. So that gives you P square by 2M, then we have plus mg into Q. So ultimately what happens is, this is how the final expression for the Hamiltonian appears. As I already told you, how do you know that this is the final expression? Is that this expression, how do you know means, this particular expression is a function of, it should be a function of Q, P and T only. Anyway, T is not there, so it should be a function of Q and P, which means dotted variable should not be there. That's the meaning. Now, since no dotted variables are appearing in the this particular expression, we think that, or we say that this is the final expression, and that's why we are putting a box. Okay, you cannot keep the dotted variable like this and put a box. You can say that you can put a box anywhere, right? So you should not place the conclusion and say that this is the Hamiltonian. So that is the point I am trying to say. First of all, you'll have to verify whether the time derivative terms are completely absent, and then everything is replaced by the corresponding momentum. Even if that happens, then you say that, okay, that is the expression for the Hamiltonian. One thing that is clear is that p square by 2m is nothing but half time m square, at least for the simple problems. So if you can now identify that the p square divided by 2m is the kinetic energy term, which is equivalent to half m square, then now we will be able to recognize that the first term is actually half mx dot square, has been appearing in a different style, but now there is a plus here. And therefore, this is the MGQ did not change its structure. So it is the same MGQ that was there in the beginning, from the beginning, and therefore that is the potential energy term that is coming. So ultimately, we are able to recognize that H is becoming kinetic energy plus potential energy if the Lagrangian is starting with kinetic energy minus potential energy. So at least when you are going to start the situation, that is, as long as you are going to consider L equal to Ke minus Pe, then ultimately it turns out that the Hamiltonian becomes kinetic energy plus potential energy. Okay, so this is but there is a point to be noted that the transformation will not be directly like this. So this is more important. Ultimately, what I am trying to say is that you may think that, okay, if this is the case, why we should do all the Legendre transformation? Simply change the minus to plus and finish the job, isn't it? But that is not always true. That is where the important point is. So even this is for simplest situation, we can easily identify that Hamiltonian is kinetic plus potential energy. But for non-simple problems such as velocity dependent potential, for example, you bring the electromagnetic potential. If you are going to bring electromagnetism here, then what happens is, in addition to the gravitational potential mg into h, you also have the electromagnetic potential. So when that enters into picture, what happens is that the dotted term, that means velocity dependent potential, will enter into picture. And in such a situation, changing this minus to plus, see, remember this one, simply if you change a minus to plus and say that is Hamiltonian, if you say that, then it is straight away that is going to be wrong. Okay, so only for very simple situations this is going to be true. Kinetic plus potential conversion is true, and therefore my conclusion that I would like to tell you is that you should never change the minus sign and plus sign and tell that you finished your job of calculating the Hamiltonian. That will not work all the time. Okay, so this calculation we have done in order to demonstrate, or in order to have a physical insight saying that in simple situations Hamiltonian can represent the total energy. To that extent, this kind of calculation is useful. But in all other cases, remember, this important conclusion is that you should always perform the Legendre transformation and get the Hamiltonian. That is the only right way of doing, and not by flipping the minus sign to plus sign. So that you never do it. In case if you do, you will always end up, most of the time when you are writing the GATE exam or the CSIR NET exam, they will not give you a question where minus is flipped to plus. So you should not do that. You always perform the Legendre transformation. So that is the conclusion based on this simple calculation. Okay, so that is the point. I think that our first point is okay now. Okay, so that means we have considered a sample situation which is fairly simple, where we can always see some other situation, especially when we take an example with electromagnetic potential. We can easily verify that minus is not at all flipping to plus. So that can be verified. Okay, if possible, I will tell something, because electromagnetic potential you are not aware of right now, because electromagnetism is there in your second semester, I think. So therefore, right now I will not jump into electromagnetic potential. So in case when we are having an opportunity to do that, I will do that one. Okay, so right now this is over. So first 3 points are over. Now we will come back to our original discussion that we have already discussed what is Poisson bracket, how to write that and standard definition. So to that extent, we have done the definition for Poisson bracket and then the purpose of the Poisson bracket. So why the Poisson bracket has come into picture, first of all, from where it came is that Poisson bracket has come into picture in the way of finding out certain constants of the motion. That is how the story started with, and we have the standard definition like this. So let me write down therefore the definition. The definition is there, I think, one or two lectures before that. We have done a general study on the determination of the constant of the motion. At that time, I have given the definition for the Poisson bracket. It is like this. So if you are going to have a dynamical variable which is A, if you also have another dynamical variable B, so it can be any dynamical variable. For example, A can be anything. Anything means what? It should represent a physical quantity. Is that exact component of angular momentum? It can be total energy, or it can be some x component of linear momentum. Okay, such kind of any of the physical quantities. That is A. B is another one. B is another physical quantity that we have. If you have two physical quantities with you for a given dynamical system, then the Poisson bracket between them is given by the partial derivatives. So I will not make the summation and then make the situation complicated. So whenever you have more number of degrees of freedom, naturally you'll have to apply the summation. So that point also I have explained in the last class. So now we are going to study the properties of the Poisson bracket, and therefore for simplicity we will not use the summation. So as and when required you use the summation, but now we will use without summation, which means we are going to make an assumption of 1 degree of freedom. So that means only one term you can write down. So how do you write? You know that. So you'll have to start with the Q first, then you'll have to do with the P. I mean Q comma P is the order that you'll have to do. Then minus Q comma P, you change the order, then we will be getting P comma Q. Okay, so we are now seeing some of the properties. Let us keep therefore this as the equation number 1. Now what you can do quickly is that immediately you can tell in the first interesting property that what happens if you are going to evaluate B comma A. So what will happen to B comma A means wherever that is the first element should be B, second element should be A, and therefore here you will have to write down the B here, and here you'll have to write down A. That's all you have to do, and then compare with the first expression. So let me write down first of all that one. So the first element should be B, the second element should be A. That is how you write down. The order QP will not change. So first will be Q, the second one will be P. So that will not change. And then here also the first one A, second one B. Now it is first one B, second one A. So I'll write down that this is dou B by dou P. Then we write dou A by dou Q. So therefore now you have this. Now if you compare this particular expression with the previous expression, what can you say? That's what we mean to say. So the product is not a these things are simple multiplication like scalar. Dou B by dou Q is a scalar. There is no vectors are not at all coming into picture. Therefore the first term dou B by dou Q is a scalar. Dou A by dou B is a scalar. Scalar multiplied by scalar, isn't it? So whether you write 2 into 5 or whether 5 into 2 is same, right? So to that extent, okay, to that extent, now you can compare the previous expression and say, where is dou B by dou Q? That is there here. Then you have a dou A by dou P. Okay, so the order is different, but however, that's what I am trying to say. This is a scalar multiplication, so these two are same. Then you can identify that this particular expression is there here. So these two are same, but second term is coming first, and therefore that is going to this side. And therefore our conclusion is that this is nothing but the negative of the equation. That is the previous equation, and I will say that that is A comma B. So it is the negative of the previous expression, which means that I can write down the compact notation. Compact notation means Poisson bracket notation. So our conclusion therefore, so this means that a straightforward calculation tells you that B comma A will be given by the negative of A comma B. So this is our equation 2, and we say that this is known as the anti-symmetry property. The property of anti-symmetry. So these properties are going to be useful to evaluate some more complicated Poisson bracket. Complicated Poisson bracket means Poisson bracket of Poisson bracket. That is what I mean to say. Complicated means, how it will become complicated means, you put a Poisson bracket inside another Poisson bracket. So then what happens is you'll have to evaluate partial derivative of the partial derivative. So like that, the situation will be slightly complicated. In such situations, sometimes you'll have to use the properties. If you use the property, it will be you can finish the calculation quickly rather than solving it without using any property. So that is where the properties of Poisson bracket is going to be very helpful. So the first one is by definition. So this is the fundamental definition. First equation is not the property. Okay, the first equation that I have written here, I'm talking about this one. So this one is the definition. Definition means this is how we start with. Let us say that a comma b is this much. Okay, then what happens? That's what we are doing. So first equation is the definition for the Poisson bracket between any two variable. If you want Hamiltonian, you can always remove the b and put the Hamiltonian there. That is okay. Okay, so this is valid for any dynamical physical quantity which must be a function of q comma p. That is very important. It has to be a function of q comma p. Otherwise, there is no meaning for the partial derivatives that we have. Okay, so first, okay, so we got one property right now. So equation number 2 is the property what is known as the anti-symmetric property. So the second, so this is the second thing. Okay, so let me therefore calculate another one. So maybe I'll write one line here. So I just want to tell that this property is completed. So just for information, so I can write down a small line here which says, the separation between one topic to the another one. So for that purpose it will be useful. Now we will consider how to evaluate the Poisson bracket of A with B plus C. So now you can understand what this Poisson bracket is. A comma B comma C, there are three physical variables are there. I have three dynamical variables for a given problem, and then I am interested to calculate the Poisson bracket between A and B plus C. So B plus C is going to be a single variable, and then what will happen if you calculate. So whenever you want to calculate any Poisson bracket, what you have to do is you'll have to use the equation number 1. That means the definition. Use the definition always. Okay, and then you can simplify. So therefore I can now write down that dou A divided by dou Q. I mean the first term here that we are writing. In the second term, B is there, right? In place of B, I will have to put B plus C. That's what you have to do. So now I'll have to put a B plus C here. Then divided by this dou P is there. So I'll write down the dou P. Then minus, you have the first element with respect to the P multiplied by the second element. Second element is B plus C divided by dou Q. And that's all. So once this expression is written, the rest of the thing is simple that you'll have to simplify. So we'll see this. This is equal to, because of the addition, the calculation is going to be simple actually. So this gives you dou A by dou Q. Then what happens is dou B by dou P plus dou C by dou P. But there is a bracket here. That is important. Then minus like this you have. So now you'll have to multiply this. Everything is a scalar, so there is no trouble with vector addition, vector multiplication. Nothing is there. They are all scalars. So to that extent, at least the multiplication and other things are simple. And now if you multiply, let me not write down all the expression, but without writing everything, you can now imagine what is happening. So there is a dou A by dou Q. There is a dou B by dou P. There is a product. So remember, there is a product. Now there is a minus. And once again, there is a product is there. You see this, there is a product again, A and B. So this is A, this is B. So I am putting 4 ticks, right? I am putting 4 ticks. So I am trying to visualize product minus product. Product minus product is the Poisson bracket. That is the definition, isn't it? Therefore, where is the product minus product? Once again, just that screen. You keep this one. This is a product. Then minus, this is another product. So product minus product is the Poisson bracket. So you have to discover whether similar structure is there here or not. So wherever I put a tick mark here, that gives you product, and there is a minus here. So therefore, I don't want to write down the all partial derivatives. Instead of that, I can write now in terms of Poisson bracket. What is a Poisson bracket now? A and B is there. So I can write down A and B and close this. Is this clear? So A comma B means what? This particular thing, maybe I'll put this. So this kind of a product, that is the first one. The second product is here. That's all. So these two products with a minus sign here, that gives me a Poisson bracket A comma B. Then there is a plus here, isn't it? So there is a plus coming here. So that plus I can put it here. So plus. So put this one plus. Then what happens? You are going to make a product of first element with dou C by dou P. And again there is a dou C by dou Q product with dou A by dou P. So that gives me another Poisson bracket A comma C. And that's all. So you got the conclusion. So our conclusion, therefore, let me write down the conclusion that the Poisson bracket of A comma B plus C is given by Poisson bracket of A with B plus Poisson bracket of A with C. So once this kind of step is clear to you, then the remaining things can be done with a reasonably you can do it quickly. And then let us have the number now. So this is the equation number 3, and we say that this property is the distributive property. Okay. So the first one that you have is the anti-symmetric property is there, and then this one you can say that this particular expression you can give the name distributive, because of course name is not very important whether you call it distributive or not calling. But what happens is, why I am giving the name anti-symmetry, distributive, etc. is sometimes this multiple choice questions when they are asking in GATE or CSIR NET exam, they may give you, or sometimes they will tell this is the property of Poisson bracket. What is the name of the property? Like this one question can come: distributive, multiplicative, anti-symmetric, or some kind of a product rule. Some name can be given as a 4th choice for you. So for that reason, getting the familiarity with the terminology is sometimes important. Otherwise, whether you know whether it is distributed or not, that's not so important, but you should know how to simplify a Poisson bracket. Okay. So the point is also important, sometimes useful for competitive examination, where 4 options can be given. For that reason, I'm also emphasizing the name here, distributive law. So once you know this, then what happens is you can go to the next one, namely instead of doing the addition, here you see B plus C is there. Instead of doing the addition, you can ask the question, what happens if I do a multiplication? So that is how you yourself can proceed further and then think about what can be done. That means we are asking the question how to evaluate the Poisson bracket between A comma the product B and C. Okay, it's a product of the 2 physical quantities. What happens to that? How do you calculate? So here the procedure is once again same. You'll have to always start with the definition. So let me quickly write down the defining equation: dou A divided by dou Q, then dou of BC divided by dou P minus dou A divided by dou P multiplied by dou of BC divided by dou Q. So here what happens is, now you'll have to use, so now you have to use the product rule. It's a standard rule, so there is nothing difficult. There are no vectors are not there, so simple scalar product rule only you'll have to use. But remember that, so you'll have to expand and write down, then you'll have to combine the terms. That's all you have to do. So dou A by dou Q multiplied by, so I'll put a multiplied by, so here I can write down B multiplied by dou C by dou P plus C multiplied by dou B by dou P. That's all. That is the UV product rule. Then you have a minus, because minus is there. You have dou A divided by dou P multiplied by B multiplied by dou C by dou Q plus C multiplied by dou B by dou Q. Close the bracket. and this is what you'll have to simplify. And remember that simplifying means you don't have to don't write all the expression once again. Okay, anyway, we don't want such a lengthy expression. That is why we are using the Poisson bracket, in fact. So now your job is don't write everything now. You search for product minus product. That is what we want. Product minus product means Poisson bracket. So tell me, where is the product minus product? So what happens is there is a b here, so I can take b common. There is a b here, so therefore I can take b common. So what I will do is I'll take a b common. If I take a b common, now I am expecting a Poisson bracket, and therefore I am using a curly brace. So you see here, I am using this particular brace is a curly brace I am using, whereas this particular one I am using a normal bracket, where the normal square bracket I am using, which means that is not a Poisson bracket. So you should be careful what bracket you are using for simplification. So in case if I put a curly brace here also, some confusion will come. Is the bracket is representing Poisson bracket or usual simplification bracket? So that kind of confusion should not come when you are performing. So if you are performing some calculation, try to use this kind of bracket or try to use this kind of bracket for the purpose of simplification. If you are going to use this kind of bracket, you have to understand that Poisson bracket, okay, not the ordinary bracket. So that part you please take care, otherwise there will be an unnecessary confusion if I am going to put a curly brace here. So that is, even though it's a minor point to be noted, it is also important, so I am telling that. So now this bracket is actually Poisson bracket, which means I am trying to I am searching for product minus product. So what products are there? You see here, AC product is there. So AC product. Do you have AC product here? It is there here, AC product. And the interesting thing is, this is PQ order. The order is PQ. Here the order is QP. So QP order here and PQ order here. Whenever that kind of a combination comes, that is known as Poisson bracket. And therefore I will write down that this is the Poisson bracket between A, C. So job is over. Then plus. Where is plus? This plus I am writing. This one. Okay. So this particular plus I am writing. Then what is left out, you see, there is a C common here. Okay. So there is a C. I'll put the tick in there downward. So I have put the tick above the variable. Now I will put the tick below the variable, so you can understand. C is here. Here also C is there. So therefore I will write down the C common. Once you C is taken common, what is left out? If C is taken common, then I have A with B. So the product is there with A and B. So you follow the white color cursor, A with B is there. Therefore, I may be able to write A comma B. Whether it is successful or not, you check here. So there is a A here. So there is a B here. So AB is there, AB is there. Here the order is PQ. Here the order is QP. So QP order followed by PQ order is there. Therefore, C can be taken outside. That is what I mean to say. So C is taken outside here. So our conclusion therefore is that the Poisson bracket between A, the product BC is given by this kind of expression. And we are not going to give a new name for that, but instead we give the same name like product rule. Because the UV product rule for differentiation is what is being used, and therefore this particular equation also we will call this as a product rule. The equation number I do not know, so please check out. Earlier one was a 3, so this one you keep it as a 4. So this is another property, very important property. This is because whenever the product comes, you should not use the UV rule and then struggle every time. The point or the purpose of studying the properties of the Poisson bracket is that you don't every time struggle and get this expression, but rather directly apply the properties and then simplify the given Poisson bracket. Okay, given Poisson bracket means what? In your question paper, one Poisson bracket will be given, and the question is that simplify the Poisson bracket. That's the question. So to finish this calculation, you'll have to use some of these product rules. It can be product rule, distributive rule, or anti-symmetry rule, or the next one that we are going to see. Okay, so the next one we will see another property. So here I will write down the interesting property is what is known as let me write down the Jacobi identity. So what is the Jacobi identity is actually, it is a Poisson bracket of the Poisson bracket. Okay, so the proof is quite somewhat lengthy, but we will not do the proof right now. But what is this identity, we will see. So this is going to be very useful to simplify certain problems. So remember, what is the Jacobi identity is all about Poisson bracket of the Poisson bracket. So I'll tell you how it is getting constructed. So you have B comma C. Let us say that I have a Poisson bracket between B and C. You know that this is one Poisson bracket. Now what you do is you put it inside another Poisson bracket. That means open a Poisson bracket and put A here and then put a comma. Now what happens? What is this? This is the Poisson bracket of Poisson bracket. That is called the A with B comma C Poisson bracket. Okay, this can be simplified. Of course, we can always use the definition and simplify, but right now that is not our aim. But interestingly, if you finish all those calculations, there is a final result coming into picture, and that final result is what is known as the Jacobi identity. Okay, what this says is very simple. It's very simple. Let me say here, if you are going to consider something like A dot B cross C is something which is familiar to you, right? So therefore I will write down that. In the standard school vectors, I mean the vector algebra, in school you studied, A dot B cross C when you study, you know the cyclic permutation. Okay, cyclic permutation means when ABC is coming, afterwards you write BCA. So now ABC is there. Okay, the first one A, second one B, third one C. So when ABC is there, then afterwards you write down BCA. BC you write down, then A you bring here. After that you write down CAB. When you write like this, this is known as cyclic permutations of the three variables. Okay, this kind of thing you already know in the vector algebra when you are evaluating some properties of vector product, okay, or volume of some kind of a parallelepiped, etc. So something you know already about this kind of ABC, BCA, CAB combination. You are going to use this kind of combination now. So now repeat the cyclic permutation. So if you repeat this, what will you get? The first one is ABC. What should be the second one? The second one should be BCA. So write down that. So this is B, comma, open bracket, C, comma, A. That's all. So this is the second term. Then plus the third one, this one. The third one would be CAB. So write down CAB. C, comma, then I have A, comma, B. That's all. You can't write more than this. Okay. So we have now completed all possible cyclic permutations of the three variables A, comma, B, comma, C, where you should remember, very important, that all the ABC represent the physical quantity and they are functions of Q, comma, P. That's very important. If it is the case, okay, if all these things are satisfied, then interestingly, why this is interesting is that such a complicated expression, if you simplify, you will get 0. Okay, so that's why it gains importance, and in many times Jacobi identity can be used to simplify certain Poisson brackets. So that is the important point to be noted. And why 0 is coming into picture? Okay, this is the lengthy expression that if you are going to expand Poisson bracket of Poisson bracket, if you expand, it is going to be a lengthy expression. But however, how 0 is coming is because of the minus sign here. See, in the definition, see, this is the definition. This is the definition. Here you have a minus sign. So that's why I told you already, the minus sign is coming here from the Hamilton's equation of motion. That from there only minus is coming here. So I told that particular minus sign is very crucial and is very important, and this is the one which is giving all these properties. The anti-symmetric property, Jacobi property, etc. These are because of this kind of minus sign which is coming to picture. So now we have this kind of basic, or what you call the simple and the standard Poisson bracket relations. So now we will make an important conclusions about this. So let me write down that. The conclusion is this. So whenever there are physical variables A, comma, B, comma, C, okay, there is no need to say ABC. Oh, there are some physical variables which follow these rules. Okay, so then our conclusion is then the dynamical variables is said to follow a Lie algebra. So let me write down that conclusion, Lie algebra. So what we are going to say is that if you are going to have variables, variable means mathematical variables, even though it represents physical quantity, ultimately it's a mathematical variable. So we are speaking mathematically. Okay, speaking mathematically, whenever we have the variables something like a comma b comma c, which are functions of the dynamical variables q and p, and if they satisfy these properties, these property means Poisson bracket properties. I mean, if all these properties are satisfied all the way from 1, 2, 3, 4, I don't know the last one, probably we'll write this as the fifth one, let us say. If all these properties are satisfied by the set of variable, then we say that the variables obey Lie algebra. That's all about it. So if you have studied some course on modern algebra, group theory, ring theory, okay, and field theory, for example, if you have studied some introduction to such kind of topics, then what this algebra is all about is that it will list properties. Okay, the first one that you must be studying is the group theory. So whenever you study group theory, immediately the first question comes, what is a group? Then immediately group is something which will satisfy the following properties. That's how you define. So what happens is, whenever you have certain mathematical variable, and if the mathematical variables obey a list of properties, that is important. You can't change the list. The list is fixed list. That list only it has to obey. If it is going to obey all the properties that are listed down there, then we say that it belongs to that group. If it is going to satisfy some other list of properties, then it is going to belong another group. So name of the group will change. It's not that everything will belong to one group in group theory. So several groups are there, and therefore we say that this obeys that group and another variable obeys another group, etc. That is what is the group theory. So similarly, in the abstract algebra, namely the group theory, Lie algebra is one similar theory that comes into picture, especially in the Hamiltonian mechanics, because only in the case of variables in Hamiltonian mechanics you have this kind of special situation. So therefore that gains interest within the physicist community. But for the mathematicians, there is much more broader area for the Lie algebra, and that is going to be modern algebra is the most general topic that we can consider, or the group theory. So let us not go into those details. Our interest is that Lie algebra is the one where the variables are going to follow the Poisson bracket relations that are shown there, and not only that, it will obey all these relations. And then we say that the variables or dynamical variables of the Hamiltonian mechanics obey the Lie algebra properties. So that will be our important conclusion. And in the next class, of course, there is a simple thing that is left out. Maybe I will try to do in the next class, or you try to evaluate. I will give the result here. Within one line you can prove this. Okay, so I'll just give this. What are you going to prove is that the Poisson bracket of q comma q is going to be 0. Okay, within one line, first line itself you will get the answer. There is nothing great here. So Poisson bracket of p comma p is 0. Okay, in case if you want to evaluate the Poisson bracket of q comma p, then you will get 1. So this is the very simple, that's why we say these are known as elementary Poisson brackets. Okay, because these are the fundamental things, or instead of saying elementary, we can also say fundamental. Okay, these are known as the fundamental Poisson brackets because q comma p is the basic variable, right? You can construct any other physical quantity based on q comma p only. So therefore, first of all, q comma p itself, what is happening? That you can easily prove. And similarly, if you are going to have multiple degrees of freedom, then you'll have to use the suffix. If there is no suffix, at least you can imagine that it is 1 degree of freedom problem. If you are going to have more than 1 degrees of freedom, then a similar relation is still valid. So let me write down that it is 0, and we can write down that pi, you'll have to use a correct symbol for ijk. So let me write down that correctly. The first one should be I, the second one should be j, that's all. Okay, there is nothing more than that. The second one, when you write, you will have to be careful that you write j. That should be equal to 0. In the second case is that for the momentum, it's pi comma pj. You can understand what do you mean by I and j. I represents p1, for example. Pj means it can be p2, p3, p4. It can be anything. That's the meaning. Some other momentum, that is the meaning. because you are going to have n number of momentum is going to be there for n number of degrees of freedom. That is why this kind of confusion can come. And ultimately, this is very important. When you are going to take Qi with Poisson bracket of Qi with Pj, if you are going to do this, you will be getting a delta Ij. Delta Ij means you already know what is delta Ij. So this should be clear to you. Delta Ij means it's a shorthand notation for either 1 or 0. Okay, how do you write either 1 or 0? You have to write either 1 or 0. You have to write without English. Without English means what? You should not use either EITHER. This word you should not write. Then how will you write either 1 or 0? So the answer is that people have discovered a symbol. Okay, let us have a symbol called delta Ij. So delta Ij is the mathematical symbol to say either 1 or 0. Then the question comes, when 1 will come, 1, 0 will come. So that doubt will come. To clarify that doubt, you say that 1 will come whenever I is equal to j, and you say that 0 will come otherwise. What is the meaning of otherwise? Otherwise means I is not equal to j. That is the meaning. Okay, so such a symbol is known as the delta symbol, which is the compact notation, or what you call the shorthand notation for either 1 or 0. Okay, so this is very important relation. These are known as the fundamental Poisson bracket relations. So PB, I will write down PB. PB means Poisson bracket. So fundamental Poisson bracket means inside the Poisson bracket you should have only Q and P. Nothing else should be there. Only then it is fundamental. If you are going to have something like ABC here, you see here, there's a A here, there's a B here, it's C here. If you are going to have anything other than Q and P, then they are known as Poisson bracket relation. Don't use the word fundamental. Fundamental means inside the bracket only Q and P is allowed. If you are going to have anything else, we say that okay, they are the Poisson brackets. Okay, they are not fundamental one. So fundamental Poisson bracket relations you'll have to prove carefully. It's very important. Within 2 lines or 1 line you can prove this. I am giving this because in the end semester examination or whatever, sometimes question will come. Prove the Poisson bracket relations for the fundamental quantities of the phase space. Fundamental quantity means why do you want to say it's fundamental quantity repeatedly? Is that in the case of the phase space diagram, I'll draw here. In the case of the phase space diagram, you see this Q will be there, and that's why here P will be there. That is why the Q and P's are known as the phase space variable. They are the very fundamental objects in the classical mechanics, and based on that, you are going to construct some other thing. So that is why this kind of terminology is very important. And finally, once you are happy with the terminology and these things, I would like to give one more terminology here. What is meant by canonical equations of motion? So it's only terminology. There is nothing new here. I'll write down that. So canonical equation of motion, or we say equations. So what are this canonical equation? Is nothing new here. So these are nothing but these are the same thing. It is same as Hamilton equation of motion. So it is just another name. Sometimes in the question paper they will tell derive the canonical equations. So you should not think that it is something new there. So canonical equation means it is the same as the Hamilton's equation. So, okay, that is the meaning. The word canonical comes only from the Poisson bracket relation. That's all. So that is the kind of terminology for Poisson bracket. So whenever you have the variables that obey the Poisson bracket relations, those variables are known as canonical variables. So therefore, based on that, when the equation is coming, the equation is known as canonical equation. That is how historically people use the terminology. So therefore, you should be clear about the terminology there. So now you know what is meant by a canonical equation. That's clear. And now next, what we will do is another terminology for clarity. Yeah, here it is. There is a Q here and there is a P here, right? So what is this Q comma P? Just now I explained that these two quantities Q comma P will be the axis that we are going to use in the phase space plotting. So that is Q will be here and this P will be here. So what happens is this Q comma P, this is known as canonically conjugate variables. So I am trying to explain the terminology. Frequently canonically conjugate will come. So you should know what is the meaning of that. The meaning is corresponding P. Corresponding is very important, okay, not randomly. So for that I will write down for clarity. If you are going to take Q1 and ask the question, what is the canonically conjugate momentum? Answer is P1. So P1 is the canonically conjugate momentum. Now once again I will explain. I have Q1. Suppose if I have P3. What do you mean by P3? You know, right? P3 means this is the momentum corresponding to the third degrees of freedom. If you have a number of degrees of freedom, you will be having P1, P2, P3, etc. So there are several P's are there, several Q's are there. So now if I am going to give a connection between Q1 and P3, can you say that P3 is a canonically conjugate to Q1? That's the question. The answer is no. No, this is not canonically conjugate to Q1. This is very important because this is 1 here and that is 3 here. So that is why it is not. Okay. You should have the same number for the suffix. Same number for the suffix is called a canonically conjugate. On one side you have the suffix I, on another side you have the suffix j, then you say that they are not canonically conjugate. So understand. So that is the point I am trying to explain. So when you have the suffix I here, then the suffix I should be there in both. So this kind of combination is known as canonically conjugate pair. Pair means Q comma P will go as a pair. Okay, why it is a pair means when you put a point here, how this point is. This is the point which I am talking about. That is why it is called a pair. Canonically conjugate pair. If you are going to write down here QI and if you are going to put a PJ here, then no, this is not a canonically conjugate pair. That's all. So these are some minor points to be noted, but however they are important, even though it's minor. The technical, or what you say, the technical terminology or the jargons, they are very important. If you don't understand the meaning of this kind of simple word, then you think that the subject is complicated, but it is not so. Okay, the topic is fairly simple. You can understand, and therefore I think this is the place where probably we can stop. Okay. If you have some additional problems with the Poisson brackets, maybe we can do it in the next lecture, or we will take another problem and then derive the Hamiltonian equation of motion for a given Lagrangian. So that can be done as another exercise. Probably we'll do that in the next class.